All right, wrapping up this chapter with synthesis. Synthesis is, again, looking at the same type of strategies we've seen. Is there a change in the carbon skeleton? Is there a change in the functional group? There are many new functional groups in this chapter. This is where I would start. I would definitely start by looking into the reactions that we have seen interconverting all four of our carboxylic acid derivatives, the acyl chloride, the anhydride, the ester, the amide. Yes, we do have some to the nitrile. No mechanisms for those nitriles. And then the overarching functional group of this chapter, the carboxylic acid. We have a lot of functional group change. Peppered in throughout all of these, we do see Grignards being able to add and add on carbon chains. So that's something to always remember as being possible. Not in this flowchart, but important for this chapter. Two kinds of carbon-carbon bond formations that we covered, Grignards being the most important, nitriles being the second as important. All right, it is useful to recall that carbon-carbon bond formation from section 13.12 that was really the Grignard reaction chapter, which we are going to be discussing a little bit more right now with identifying other functional groups, right? Grignards are really, really important, and we are going to continue looking at Grignards in chapter 21. Essentially, this alpha carbon right here, this is the carbon atom that is functionalized, the one that is created in step number 1 here with the magnesium as the Grignard reagent, right? It's that beautiful new carbon nucleophile that we are talking about. We've seen a lot of carbonyl atoms being able to add on this Grignard reagent. However, any old electrophile that we have ever seen, epoxides, can also be used, right? Recall that epoxides are very reactive to either acid or basic conditions. This is a base, right? Basic condition here, because it is looking at a carbon with a negative charge. And so that epoxide can be reacted at either carbon 1 or 2 of the epoxide. If we are basic conditions, we typically react at carbon number 1. So that new bond is being formed. Why? Because of steric hindrance, the less substituted gets attacked by a good nucleophile. And then a water workup is used to clean up the alcohol that forms. Now, when forming new carbon-carbon bonds, it's really critical to make sure that we're counting our carbons. So I would highly recommend looking at what type of functional groups are present and counting up the carbons. A carbon from a Grignard reacting with a carbonyl usually adds that 1 carbon. This is something that's thrown into the book as practice problems, and I want you to be aware epoxides are electrophiles that we've used before, right? So they are still valid electrophiles for our Grignards, even though they're not super prevalent. Doing a little bit of spectroscopy. Don't forget, we do have spectroscopy going on in every section. CO stretching still, just like we saw in chapter 19. Now we just have different functional groups. This chart is pretty important to be able to start differentiating the range of carbonyl signals. Remember, conjugated carbonyl signals appear lower wavelengths, around 40 centimeters to -1 less than a saturated carbonyl. So that wave number is slightly lower for our chapter 20 carboxylic acid and their derivative molecules. The OH stretch of an acid gives that very broad peak, so carboxylic acids tend to be a little bit more easy to define. The carbon-nitrogen triple bond stretch is relatively easy to see, around 2200 centimeters to the -1. Carbonyl peaks on IR are difficult, but on carbon-13 are very easy to identify. So those carbonyl peaks can help you identify, can be identified with carbon-13, or even proton NMR as well, right? Proton NMR, the carbonyl of a carboxylic acid is easier to see. Nitrile carbon-13, just remember it is a sp hybridized carbon, so it appears in the middle right around 115 to 130. Let's just predict the number of chemical shifts for all these lovely carbon-13 carbons in this molecule. And let's predict the number of proton NMRs, okay? So when we're looking at this, we want to just start predicting and seeing if there's symmetry. Well, there's not symmetry in this. So let's first do the carbon-13 and identify this carbon would most likely be the furthest downfield, and this one, right? 3, 4, 5, 6, 7, 8 would all be in the range of our sp2 aromatic compounds. 9, 10, a little bit further upfield. So there are 10 carbons. They will be all different. We'll see the furthest downfield will be 1 and 2. The ones right in the middle will be 3, 4, 5, 6, 7, 8. And the furthest upfield will be 9 and 10. Beautiful. Now let's go ahead and do the proton. Right? Let's draw in all of our other hydrogens so that we can see how many there are, where they are, what's going on, where should they show up. Nice. Well, we definitely expect this guy to show up around 12 ppm. He'd have an integration of 1H, and he'd be a singlet. He has no neighbors. He's also attached to an oxygen, so he doesn't split or go into splitting. I'm going to call this proton 1H, 1H, and 1H. There's not really a lot that we can talk about with the aromatic cluster. It would probably be around 7 ppm for all of these. It would not need you to differentiate the splitting on these aromatic protons. Most likely the, I'll call this A and B and C. Most likely A and B would be splitting each other into a doublet. However, C might be merged in there, so it would be not symmetrical and rather messy. All right, there are no chiral centers on this molecule, so that CH2 group, the methylene group, would have an integration of 2H. It would most likely be a triplet, and it would probably be shifted a little bit because of the benzene ring, and also it is beta to a carbonyl, and so we most likely should see starting around 1.2 ppm plus at least 1/5 added, so another 0.2. So we're looking at a shift of around 1.4 to maybe 1.5, depending on what the aromatic compound does, ppm. This methylene group would also be 2 hydrogens. It would also be a triplet because of its 2 next door neighbors, the 2 hydrogens we just talked about. It is alpha to that carbonyl group, so it would be shifted downfield a whole 1 ppm, which means that we would expect it around 2.2 ppm. Beautiful. So 1, 2, 3, 4, 5, 6 signals for the proton NMR, for a total of 1, 2, 3, 4, 5, 6, 7, 8 protons. Awesome.